Good afternoon, everyone. My name is Jackie Rudisell. I'm an MLT working at a local hospital here in Hickory, North Carolina. I'm also pursuing my CLS degree through Winston-Salem State via their online distance education program. My presentation this afternoon will be on CRISPR interference in regards to E. coli, specifically E. coli 12. As you'll see, I've provided my poster board with the actual presentation, a few pictures, as well as a handout of the photo board and some literature review as well as references. CRISPR-Cas is a common immune system that can be found in prokaryotes. It's a highly adaptive system that joins short strands of DNA that originate from the attacking nucleic acids into genomic CRISPR loci. These loci, in a sense, are like secondary immunity in that they remember the characteristics of the invaders. The transcripts of genomic CRISPR loci found in E. coli are split into smaller sections of RNA. The cascade complex then uses the small sections of RNA to tie the DNA of the invading organisms. The quality of the DNA is then lessened during the CRISPR interference by Cas3, or the Cas3 cascade complex. The immune system of the prokaryotes has become highly evolved. CRISPR-Cas is the name of a highly evolved adaptive immune system. The scientific name for the abbreviation is clustered, regularly interspaced, short, paleochronic repeats, and CRISPR-associated protein. Genomic CRISPR loci have some of the invader's genetic material combined with them. This, in a sense, gives them a memory of what they're looking for if invaded again. The genomic CRISPR loci are now able to remember the invading viruses and plasmids. If these same viruses or plasmids invade the prokaryote again, the genomic CRISPR loci will remember them when they express their genetic material as small RNA molecules. The immune system is then activated, and the Cas protein complexes are then routed to the nucleic acid sequence of the viruses or plasmids. Research has shown that scientists were able to cure E. coli K12 by integrating new spacers into two CRISPR loci. Under non-selective conditions, in a CRISPR-mediated way, cured clones were integrated in at least one but up to 5 antiplasmid spacers in genomic loci. These spacers were selected in a non-random fashion to target all of the protospacers that contained an AAG protospacer, a joining image. They are located just before the prospacer. Observations of co-occurrence of PAM deviations and CRISPR repeat mutations were made. This indicated that at least one nucleotide of the PAM was incorporated. The nucleotide was placed as the nucleotide of the repeat when a new spacer was added. When there were several spacers added in a single clone, it caused all the spacers to target the same strand of plasmid. And this is much like you're seeing in the pictures. You've got the cutting, the interference, the adaptation, the biogenesis, and you just see where they clip in and add a new spacer. The recognition of foreign DNA, the invading plasma, the Cas complex, and an integration of a new spacer is added into the line of protospacers. This has led scientists to believe that CRISPR interference that is caused by the first spacer later added spacers to take over events in a strand-specific manner. It is concluded that resistance against bacteriophage infections and removal of residing plasmids is provided by the type IE CRISPR-Cas system of E. coli, the required spacers. And you can take a look again. Basically, the invaded space of the RNA is clipped out, removed from the sequence, which causes the invader's plasmid to no longer exist within that strand. And that is basically how the E. coli K12 was cured. I hope you've enjoyed my presentation. If you have any questions after the presentation, please feel free to let me know. Again, thank you.